Black holes are by right considered some of the most fascinating and mysterious objects in the universe. And while we now know they are real things that exist and we can study them to an extent, they were long believed to be mathematical curiosities, born from Einstein's theory of general relativity. And in the first half of the 20th century, a lot of scientists didn't believe they could be real, including Einstein himself. However, the concept of black holes as these strange bodies so massive that their immense gravitational pull won't let anything escape actually goes all the way back to the 18th century. In 1784, English scientist John Michell was the first person we know of to consider a celestial body so huge its gravity would not allow any emitted light to escape. The surface escape velocity would be greater than the speed of light, and so the object would be completely dark and invisible. Mitchell correctly noted that such supermassive but non-radiating bodies might be detectable through their gravitational effects on nearby visible bodies, which is an incredibly accurate prediction because in the modern age this is one of the only ways we have to find black holes. A few years later, in 1796, independently from Mitchell, French scientist Pierre-Simon Laplace mentioned that a star could be invisible if it were sufficiently large, while speculating on the origin of the solar system in his book Exposition du système du monde. He also provided mathematical analysis when asked for it, but you have to keep in mind that in his time, scientific consensus on the nature of light was that it consisted of very tiny particles, so Laplace's analysis was incorrect, but still the concept was there. Other scientists in Mitchell's and Laplace's time were initially excited about the idea of giant but invisible dark stars hiding in plain view. But the enthusiasm waned when it was discovered that the nature of light seemed more wave-like, and it was then unclear what, or if any influence gravity would have on light waves. Now, fast forward to 1915, the year Albert Einstein published his theory of general relativity and revolutionized science. Newton's old law of universal gravitation describes gravity as a force by stating that every particle attracts every other particle in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers of mass. Essentially, time and space were considered the passive stages on which objects exist and attract each other depending on how big they are and how close they are to each other. What Einstein did was refine Newton's law by proposing gravity is a geometric property of space and time, or four-dimensional space-time, and the gravity of massive objects bends space and therefore time, since they are one and the same. Einstein's field equations relate the geometry of space-time to the distribution of matter within it. To give an example, using Newton's law, you will be able to mathematically describe how massive bodies like the Earth and Moon orbit each other. General relativity adds to that and tells you how their mass affects both space and time. Now, Newton's law is still valid for most everyday physics. It can still very much be used as an excellent approximation of the effects of gravity, like the Earth-Moon dynamic. General relativity really only comes into play when you need to be extremely accurate or when dealing with extremely strong gravitational fields like black holes or at small distances. One example of that is the way the sun's gravitational field affects the orbit of Mercury in such a way that Newton's law cannot predict it accurately. But general relativity can, because it considers the geometry of spacetime and how the sun's gravity curves it, and has a small but noticeable effect on Mercury's orbit. Another example of this that is much more relevant to our modern daily lives on Earth, time for satellites in low Earth orbit effectively runs a teeny tiny bit faster because they are farther away from things on the surface. Earth's gravity affects space-time enough that engineers building satellites, for example for GPS systems, need to take general relativity into account. Otherwise, the satellites won't remain synchronized and GPS just wouldn't work, since time passes ever so slightly faster for the satellites in orbit than for the systems on the ground. So you couldn't provide accurate coordinates for a GPS and it would give you wrong information. Okay, back to 1915. Now, physicists and mathematicians had work to do with Einstein's brand new theory and his field equations. Keeping in mind, the concept of black holes as we understand them today was still in its infancy. And so, nobody was really looking to prove they existed. Also, it wasn't like scientists readily accepted Einstein's radical new theory. Being scientists, they had to test it, of course. And the total solar eclipse of May 29, 1919 helped them confirm general relativity's prediction of the deflection of starlight by the sun's gravitational field, instantly making Einstein famous. As it turned out, gravity can very much affect light. Still, while clearly being superior to Newton's law, the theory remained outside of mainstream theoretical physics and astrophysics for a few decades. Mostly because it was considered something of a curiosity among physical theories. There just didn't seem to be much you could really apply it to in the real world. The kinds of massive gravitational fields you could use general relativity for had not been observed anywhere in the universe, and so a lot of scientists were doubtful they even existed. Either way, some physicists had fun with the math. Yeah, really, they did math for fun. Einstein's field equations are considered very difficult to solve, and Einstein himself used approximation methods in working out initial predictions of the theory. But already in 1916, German astrophysicist Karl Schwarzschild found the first exact solution to the field equations, which was later named the Schwarzschild metric, or the Schwarzschild solution. It mathematically describes the structure of spacetime around a stationary, non-rotating spherical object with no electrical charge. The peculiar thing with Schwarzschild's solution was that it seemed to suggest that a mass gathered in a small enough space would lead the equation to blow up to infinity, and so there was a lot of confusion about the nature of these so-called singularities found in the Schwarzschild solution and other solutions to the field equations. Right at this point in time, the groundwork for the idea of a black hole as we know it today was being laid out, but nobody quite understood what it truly meant and what to do with it, so the concept was mostly overlooked by physics. I say mostly because some physicists were trying to make sense of what these solutions to the field equations implied, slowly but surely realizing what general relativity could predict about the final stages of evolution of stars. Keeping in mind stellar evolution and how stars generated energy in the first place were still not well understood at this time. Scientists knew gravity made gas and dust in space collapse into stars, but it would still be another few decades before they discovered and could prove it was nuclear fusion that countered gravitational collapse and made that stars can shine for millions and billions of years. In 1931, the young Indian-American physicist Subrahmanyan Chandrasekhar calculated that an object made up of degenerate matter with a mass greater than 1.4 solar masses has no stable solutions. What that applies to is white dwarf stars, the leftover cores of stars after their deaths. White dwarfs don't have a heat source to counteract the effects of gravity like regular stars do, but a quantum effect called degeneracy pressure prevents them from completely collapsing, up to that limit of 1.4 times the mass of our Sun. This was another prediction using Einstein's relativity that went underappreciated at the time. Scientists knew about the Schwarzschild metric, and the emerging field of quantum mechanics helped astronomers find out more about the nature of the white dwarfs they observed in the universe, and would ultimately help them discover that nuclear fusion is what makes stars shine. But also, a lot of scientists found it a pretty absurd idea that it was theoretically possible for an object that could completely collapse under its own gravity to exist. It was argued that some yet unknown mechanism would ultimately stop the collapse, and to be fair, they were partially correct. We now know that a white dwarf slightly more massive than the Chandrasekhar limit will collapse into a neutron star, which is stable. Back in the 1930s, a few people were doing serious work on continued gravitational collapse, but a clever young scientist by the name of J. Robert Oppenheimer took up an interest in astrophysics. Along with his friend Robert Serber, he wrote a paper exploring the properties of white dwarfs, and later, along with a student of his, George Volkoff, he wrote a paper in which they mathematically demonstrated that, above a certain mass limit, neutron stars would not remain stable, and would undergo gravitational collapse anyway. Oppenheimer and another student of his, Hartland Snyder, wrote a paper titled On Continued Gravitational Collapse in 1939, in which they, for the first time in history, used general relativity to show how a black hole could develop. Ironically, in the same year, Einstein used his own relativity theory to attempt to prove that black holes could not exist. This was another important step in black holes becoming a proper topic of research in the future, but maybe you've guessed it, at this time the research still went largely unnoticed by the broader scientific community. Between the 1940s and 1950s, the focus of physicists went more to discoveries in quantum mechanics and nuclear physics, which led to the development of the atomic bomb, but also amazing new technologies such as transistors and lasers. It wasn't until the 1960s that researchers began to really tinker with the Schwarzschild solution and its mathematical oddities, though they were still a pretty long way away from thinking of black holes as real objects that exist in the universe. But they did start to understand that the math pointed to a point of no return, the event horizon. Now, we already had John Mitchell and Pierre-Simon Laplace speculate that light would not be able to escape from a body that's massive enough. Now, scientists were realizing Schwarzschild solution showed that this was something that was theoretically possible. In 1958, David Finkelstein first published the interpretation of the black hole idea as a region of space from which nothing can escape, calling it a perfect unidirectional membrane. Casual influences can cross it in only one direction. That means that events that occur inside of the black hole, so beyond its event horizon, can't affect events that occur outside of the black hole. And so black hole theoretical physics entered a golden age in the 1960s and 1970s. It began when physicists found more solutions to Einstein's field equations. The Schwarzschild solution only applied to a stationary, non-rotating black hole with no electrical charge, but physicists Roy Kerr and Ezra Newman found solutions for black holes with angular momentum and electrical charge. These findings resulted in the so-called no-hair theorem. It states that a black hole can't have externally observable characteristics aside from its mass, angular momentum, and electrical charge. Any other features, such as its geometry or what kind of matter the star the hole collapsed from was made of, is information stuck or lost behind the event horizon. A black hole has no hair was the phrase coined by Jacob Bekenstein to emphasize the almost featureless nature of black holes. The next extremely important development in black hole science was Roger Penrose's work. He found an innovative new approach to the mathematical tools used to analyze the properties of space-time. His 1965 paper, Gravitational Collapse and Space-Time Singularities, can be roughly summarized as that if an object, such as a dying star, implodes beyond a certain point, then nothing can prevent the gravitational field getting so strong as to form a singularity. Or rather, that is the mathematical result of Penrose's work. Because of the nature of the event horizon, there doesn't seem to be any way to find out what happens beyond it, so we really can't find out if a singularity is a physical real thing as such. However, Penrose's work led to Stephen Hawking using his approach to show that the universe itself may have begun as a singularity, in his 1966 paper, The Occurrence of Singularities in Cosmology. That is to say, in theory. At this point in history, we're still very much in the phase of black hole science that they were entirely theoretical objects and nobody knew for sure they could exist in the universe. A lot of the math checked out and made for some fun ideas about the bizarre nature of objects undergoing continued gravitational collapse. On paper. Until 1967. Astronomical observations also made great strides during this era, and the development of astronomical observations in other wavelengths than visible light, like radio and X-ray astronomy for example, would be of huge importance. In 1967, Jocelyn Bell Burnell, while conducting research for her doctorate, discovered peculiar signals in the data gathered by a radio telescope she helped build. It was initially dismissed as radio interference, but the nature of the signal soon proved it couldn't come from Earth. For a little while, it was suspected that the signal may indicate extraterrestrial intelligence, but then Jocelyn discovered another object just like it, and many more would be found in the coming decades. By 1969, these objects were shown to be rapidly rotating neutron stars and were dubbed pulsars, short for pulsating radio source. Until that time, neutron stars, like black holes, were considered just theoretical curiosities born from general relativity taken to its extremes. But the discovery of pulsars spurred further interest into all types of compact objects that might be formed by gravitational collapse. In the early 1970s, work by James Bardeen, Jacob Bekenstein, Brandon Carter, and Stephen Hawking led to the formation of black hole thermodynamics. These laws describe the behavior of a black hole in close analogy to the laws of thermodynamics by relating mass to energy, area to entropy, and surface gravity to temperature. The analogy was completed in 1974 when Hawking showed that quantum field theory implies that black holes should radiate like a black body with a temperature proportional to the surface gravity of the black hole, predicting the effect now known as Hawking radiation. So essentially, a black body is an idealized physical object that absorbs all electromagnetic radiation, so a perfect black thing. But such an object will still emit radiation because of entropy. In somewhat oversimplified terms, that means the energy in an enclosed physical system is always going to even out as much as possible. So in nature, a black hole is a near-perfect black body. A perfect black body doesn't exist because it is a mathematical concept. And before Hawking's 1974 paper, it was generally assumed that black holes would not emit any radiation due to the nature of the event horizon. Once any particle of any kind goes past that, it can't come back. And even Hawking himself believed this until he made that paper and did that research and found out it is possible for black holes to radiate energy. Right, if I want to explain Hawking radiation, the next thing we need to understand a bit better is quantum mechanics. Because of the uncertainty principle, all the exact properties of any given particle can never be all known at the same time. Say you want to measure its speed, you become more uncertain of its position, and vice versa. So, on the quantum scale of things, the amount of energy in a point in space will randomly fluctuate. Particles will pop in and out of existence, so to speak. Keeping in mind they're not particles, like we like to imagine them as tiny, tiny balls, but there's these sort of packets of energy, quanta from the singular quantum, that interact with each other in specific ways. And we call these interactions the fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. And the particles that carry the forces, the quanta, are photons, electrons, W and Z, and Higgs bosons, and so on and so forth. Now, Hawking radiation is caused by pairs of particles popping up right on the edge of the event horizon of a black hole. Normally, a pair of these virtual particles would pretty much immediately annihilate each other. These tiny fluctuations happen everywhere all the time. Right at the event horizon, however, it could happen that one particle falls in and the other escapes as radiation before they can annihilate each other. Now, because these particles appear from these random energy fluctuations and instantly disappear again, usually that's okay because the amount of overall energy stays the same over time. In case of a pair getting separated near the event horizon of a black hole, a tiny amount of energy gets taken away from the black hole. And so over extremely long periods of time, if the black hole does not get energy from anywhere else, like by material from space falling in, it will shrink and evaporate. Hawking radiation would be so incredibly weak, it's impossible to detect it in space with our current technology. Because it just won't happen all that often that a pair of particles pops right up at the exact place near a black hole's event horizon to steal the tiniest amount of energy from it. Alright, back to the 1970s, where physicists and astronomers were starting to find actual evidence of black holes truly existing out there in space. 7,300 light-years away in the northern constellation Cygnus, scientists had discovered a strong X-ray source, one of the strongest detectable from Earth's orbit. X-rays barely penetrate Earth's atmosphere, so discovering sources of this high-energy radiation was not possible before the development of spaceflight, even though X-rays themselves have been a field of scientific study since the late 1800s. The X-ray source was dubbed Cygnus X1. Unlike stars or pulsars, it was not associated with any prominent radio or visible source. In 1972, it was discovered that Cygnus X1 was actually a binary system with the supergiant star HDE 226868. Using the emission patterns of the visible star, research teams found that the mass of Cygnus X1 was likely too large to be a white dwarf or a neutron star, indicating that it was probably a black hole, and further research has only strengthened this hypothesis, and so it became the first object to be commonly accepted as a stellar mass black hole, formed from the gravitational collapse of a giant star, and is now one of the most studied astronomical objects in its class. And so, a somewhat vague scientific concept from nearly 200 years ago became reality. And it's a great example of the power of the scientific method and how research and knowledge built over several decades and centuries even can give us answers to questions that seemed impossible to answer at first. Now we're not quite done, and for sure, scientific research into black holes is far from done, and there are many questions that don't have answers as of yet. The next problem for scientists to crack was finding proof of the existence of supermassive black holes, ones with masses many times that of the Sun, from hundreds of thousands of solar masses up to billions. With the development of astronomy and all wavelengths of the electromagnetic spectrum in the first half of the 20th century, scientists found enormous sources of energy deep in space that they had no good explanation for at first. These sources turned out to be millions and even billions of light years away from our galaxy. And since they seem to have different properties from regular stars, they were dubbed quasi-stellar radio sources, or quasars for short. Although we now know quasars radiate energy in all wavelengths. The energy output of these quasars is truly gigantic, but because they're so far away, they can appear as small stars from Earth. In reality, they outshine the galaxy they're in and are many times brighter than the millions of stars surrounding them. Initially, astronomers had no idea why quasars seemed so distant yet so highly energetic, since back then in the 1960s and 70s they didn't know of any mechanism that could explain them. With evidence of black holes actually existing being found, the idea of supermassive black holes began to take shape. Quasars could be explained by material and gas accreting around a black hole many times more massive than any star, and that infalling gas would speed up and get heated up to millions of degrees. The following decades, more evidence was found that quasars are indeed supermassive black holes in the hearts of galaxies, and observations suggest that almost every large galaxy has a supermassive black hole at its center, though not all of them are quasars. The supermassive black hole in the center of our galaxy, Sagittarius A star, is not a quasar. Its energy output isn't high enough for that, and quasars appear to have been more common in the distant past of our universe, about 10 billion years ago. The next revolution in black hole science has less to do with discoveries about their strange properties, but more with the influence they have on their environment, namely gravitational waves. Minute distortions or ripples in space-time itself. They're produced by cataclysmic events like neutron stars colliding, supernova explosions, events occurring in the early days of the universe shortly after the Big Bang, and black holes emerging. The existence of gravitational waves was already an idea back in the late 19th and early 20th century, but it was once again thanks to Albert Einstein's theory of general relativity that scientists had a mathematical framework to predict them. General relativity interprets gravity as a consequence of distortions in spacetime caused by the presence of mass, and so certain movements or acceleration of these masses will cause ripples spreading out from the source at the speed of light. Einstein himself considered this mostly a curiosity, since he understood that these ripples would be far too minuscule to detect using technology foreseen at his time. Due to the law of conservation of energy, the energy radiated away by gravitational waves from a system of two objects orbiting each other would cause them to slowly spiral inwards, an effect that would be extremely tiny and challenging to observe. But we did it anyway. In 1974, Russell Allen Hulse and Joseph Taylor Jr. provided the first experimental evidence for the existence of gravitational waves by observing two neutron stars orbiting each other. Actually the first pair ever discovered. The orbit of this binary system is slowly shrinking as it loses energy because of the emission of gravitational radiation. The rate of the shrinking can be precisely predicted using general relativity, and over the course of the next 30 years, Taylor, Hulse, and colleagues made measurements that matched this prediction better than 1% accuracy. Now, being that accurate in scientific terms makes many physicists and scientists very, very, very happy. Hulse and Taylor won the 1993 Nobel Prize in Physics for their work. Obviously, gravitational waves will be the strongest coming from massive objects such as neutron stars and black holes, and particularly when binary ones merge due to the loss of energy as they spiral inwards to each other. At the very end of this process, the two objects will reach extreme velocities, and in the final fraction of a second of their merger, a substantial amount of their mass would be converted into gravitational energy, and travel outward as gravitational waves. Big waves like that would be easier to detect, but for a long time little was known about the number of compact binaries in the universe, and reaching that final stage can take millions of years. So there was a lot of uncertainty as to how often events like that can happen. You can imagine even big gravitational waves would need very precise measurement methods and a way to separate the waves from other things vibrating on Earth. Already in the 1960s, scientists figured lasers could be used to try and detect gravitational waves, but it would take decades to conceive and build sensitive enough detectors. The Laser Interferometer Gravitational Wave Observatory, or LIGO for short, built by Caltech and MIT in the United States, has been operational since 2002. Essentially what LIGO does is split a laser beam in two directions down 4-kilometer-long tunnels, or arms, bounce off a mirror at the end of each arm, and the light comes back to the beam splitter. The gravitational wave will affect both arms differently. One will contract ever so slightly, and the other will extend ever so slightly as the wave passes through, and so this will also affect the laser beams. When the laser beams return without a gravitational wave disrupting them, the light waves will not be changed and cancel each other out. If the arms are being disturbed by a gravitational wave, the light waves will be different, and that's a difference we can detect and gain important information from. Finally, in 2015, LIGO made the first direct observation of gravitational waves given off by the merger of two black holes with 35 and 30 times the mass of the Sun, about 1.4 billion light-years away from Earth. Not only confirming the existence of these waves, but also the existence of binary black holes and the fact they merge. This was all mathematically predicted, but this direct observation is one of the biggest scientific discoveries of our time, and easily one of the biggest scientific discoveries ever. And it provided us with a brand new way to make observations in the universe. Before, all observations, everything we know about the universe, have been made by observing the electromagnetic spectrum, light waves, but now we can use ripples in space-time itself to study things that were previously impossible, like violent astrophysical events such as black hole mergers in deep space. And this could help scientists create more precise models of the history of the expansion of the universe and the nature of the dark energy that seems to accelerate it. We would also be able to finally see the earliest days of the universe. Back then, the newborn cosmos was so highly energetic that most matter was ionized and photons were scattered by free electrons. Light could not shine as such because it was all just loose particles bouncing off each other like really wriggly and extremely hot soup. The universe expanded and cooled off and would go completely dark until gravity made gas clouds collapse, igniting nuclear fusion in their cores, and so the first stars began to shine. With just light, we can't see past the first stars in the early days after the Big Bang. But gravitational waves aren't affected by the Wrigley soup, so we can potentially make observations of gravitationally significant events of that time. This is huge. This still blows my mind. It's been years and it's still just really just... The next chapter in black hole science was trying to take a picture of one. The question of what a black hole could look like goes back to the 1970s once it became apparent black holes weren't just mathematical curiosities but real objects in space. Now you can imagine finding a black hole, an object that doesn't emit any detectable radiation, is pretty hard. As we've seen, the first black hole ever was found by the effects it has on its surroundings, and that is generally how scientists still find them, though they now also have gravitational wave detection. Still, most black holes known were found by how they affect their environment. The central black hole of the Milky Way, for instance, we know is there because we can see a seemingly empty, dark spot where all of these stars are orbiting around as if they were circling a really dense mass. Another way is observing the energy released by infalling matter getting superheated as it spins around the black hole, like we've seen with quasars. For the last about 40 years, however, the only means scientists had to try and imagine what a black hole could look like is math. Yeah, it's always math. The first person to attempt to simulate a black hole image was French physicist Jean-Pierre Luminet, back in 1978, using nothing but good old math, an early transistor computer with punch card inputs, a piece of paper, and ink. The thing with black holes is they, in some sort of way, really are holes. That is to say, they're not spherical balls like stars or planets. The event horizon is not a thing you can touch as such, but a limit to the information escaping beyond that point, and a black hole's mass curves space-time to an extreme degree. So extreme that photons that normally travel in a straight line through empty space get bent around the hole, so background stars would show up around the black hole several times. Jean-Pierre Luminet made the first simulation of a black hole with an accretion disk, so somewhat similar to a planet with rings. You get a sphere, but not really a sphere, with a ring of glowing material going around it. But the fun part is that the image of this ring of hot material is bent around the black hole several times due to the extreme gravity and becomes distorted. And so you would see this effect, and now that has become a well-known image of a black hole. Luminet's first image that he drew in dots corresponding to calculations he made is, as you can see, accurate because naturally other people have tried their hand at simulating black holes many times, including for a movie. Now, after 40 years of simulating black holes, on the 10th of April 2019, the first direct image of a black hole and its vicinity was published, following observations made by the Event Horizon Telescope in 2017 of the supermassive black hole residing at the heart of the Messier 87 galaxy. Messier 87 is an enormous elliptical galaxy containing trillions of stars. Compare that to the Milky Way that has between 100 and 400 billion stars, and is located about 54 million light-years away from us. The core of the galaxy shoots a huge jet of material out into deep space, and scientists suspected this jet comes from a supermassive black hole at the center. Now, to image a black hole that far away, at the heart of a glowing galaxy, takes a telescope that is bigger than any ever built. So big, in fact, that you could not possibly build one telescope to do this. So the Event Horizon Telescope isn't one telescope as such, but rather several telescopes located all over the Earth linked together to gather information. 8 observatories in 6 different locations looked at M87 for 4 days and gathered a total of 5 petabytes of data. A lot of processing later, this is the result: the black hole's emission ring and the shadow at the center. Keep in mind that the shadow is not the event horizon. That is hiding deeper in there. The event horizon absorbs any light emitted by objects behind a black hole, so that light doesn't reach an observer, but the extreme gravitational field bends and magnifies background images, and so the shadow appears much larger than the event horizon due to this magnification effect. In 2022, the Event Horizon Telescope collaboration released an image of the black hole at the center of the Milky Way. It has also observed other extreme objects in deep space like other black holes in galaxy centers and quasars. And all this data will allow scientists to learn more about these things. The Event Horizon Telescope isn't the only way we find black holes. The European Space Agency's now retired Gaia spacecraft was in service for 11 years and was specifically designed to measure the positions, distance, and motion of stars and exoplanets. In 2023, it found a black hole orbiting a Sun-like star about 1,500 light-years away from Earth, and this is the closest black hole we've found so far. But black holes remain mysterious and elusive, and there's a few open questions still, like the black hole information paradox. You'll remember the O'Hare theorem from earlier in the video, and according to that, a black hole is defined only by its mass, charge, and angular momentum. This seems to mean that all other information about the previous state of the black hole, what kind of star it was, and what it was made of, is lost. Back when scientists thought black holes persist forever, this wasn't really a problem, since you can assume that that information still exists beyond the event horizon, it's just inaccessible. But now we know they slowly evaporate through Hawking radiation. This radiation doesn't appear to carry any additional information about the matter that formed the black hole, so it would seem that the information is just gone forever. That goes against a core principle of both classical and quantum physics, that you should be able to determine the past or future state of a system by looking at its current state. It would seem that the information is preserved in some type of way, however, scientists just haven't figured out in what way for the time being. It seems the answer could be revealed by finally finding out how general relativity and quantum mechanics are linked together in an overarching theory, but there is none of this coming as of yet. So the paradox seems to stem from our lack of knowledge. So it's not a paradox as such, we just don't have all the puzzle pieces to complete the picture. To be continued. Another unanswered question concerns supermassive black holes in the early universe. Some of the extremely bright quasars powered by supermassive black holes that have been observed existed as early as 670 million years after the Big Bang. And these quasars seem to be too big to have formed from the first stars collapsing. So scientists are looking for different mechanisms that may have produced these enormous quasars so early on. One idea is that several, probably many, smaller black holes merged to form these supermassive ones. It's also possible black holes collapsed directly from enormous and extremely hot clouds of gas in the early universe without even forming stars first. In the current era of the universe, conditions needed to form black holes are rare and are mostly found in stars, but in the early universe, black holes may have formed differently. Namely, from fluctuations of space-time itself before stars even existed. These are called primordial black holes, but the models of the early universe shortly after the Big Bang vary wildly, so primordial black holes may have been very tiny or huge enough to have been seeds for the supermassive black holes we can currently observe in some of the earliest galaxies found so far. To be continued. Alright, that concludes the history of the scientific study of one of the most fascinating objects we have found in space. Hopefully, all the remaining questions will be solved in the near future, and as we've seen, science is a continuing process of building a giant castle of human knowledge, brick by brick. Thank you for watching this video. I hope you learned something new today, and I will see you soon.